Why are C++ segmentation fault stack traces so complex? Imagine trying to solve a mystery where the clues are hidden deep within a maze of code. When a C++ program crashes with a segmentation fault, the stack trace is like a map of that maze. But why does it often look so confusing? The reason is that segmentation faults happen because of illegal memory access, which can occur from where the actual mistake was made. In C++, you work directly with memory using pointers. If you dereference a null pointer or an uninitialized pointer, the program tries to access memory it shouldn't. The stack trace then shows the chain of function calls leading up to that illegal access. But that chain can be many layers long, making it tricky to find the original problem. Another factor is that C++ compilers often optimize code to run faster. These optimizations can change how the code appears during debugging. Functions might be inlined, or code might be reordered, so the stack trace doesn't always match the source code exactly. This makes it harder to follow the trail of errors. Memory corruption is another cause of complex stack traces. For example, buffer overflows or stack overflows can silently damage memory before the crash happens. When the program crashes, the trace shows where it was detected, but the root cause might be earlier in the program, hidden behind layers of corrupted data. Deep recursion or large call stacks also make traces longer. If a function calls itself many times, or if there are many nested function calls, the trace can become overwhelming. Without tools to analyze these long traces, pinpointing the exact cause can be like finding a needle in a haystack. C++ does not automatically check if you are accessing memory within bounds or if your pointers are valid. This means faults can happen from where the actual mistake was made. The stack trace then becomes a puzzle, showing the crash but not always revealing the original error. To tackle these issues, developers use debugging tools like GDB or LLDB. These tools let you see the exact point of failure and examine memory at that moment. Sanitizers like Address Sanitizer can detect invalid memory accesses early, giving clearer clues. Writing safer code with smart pointers and bounds-checked containers reduces the chances of faults happening in the first place. Analyzing core dumps can also help you see the program state after a crash. Understanding that C++ segmentation fault stack traces are complex because they reflected deep, layered memory issues helps you approach debugging more systematically. Using the right tools and practices, you can entangle these traces and find the real cause behind the crash.